In the endless vastness of space, countless stars fill the universe. Yet one star stands out, lighting up our sky and shaping our lives: the Sun. It burns brightly at the center of our solar system, its light both amazing and essential. It's no surprise that ancient people, fascinated by its fiery glow, created many myths and stories to explain its power. Today, with technology far beyond what they could have imagined, we can study the Sun like never before. By looking at it through different types of light, we have found something out of the ordinary. The Sun is changing. This incredible image was captured by NASA's Solar Dynamics Observatory, SDO, a space mission launched in February 2010. The mission was designed to uncover more about how the Sun's activity affects life on Earth and our technology. By studying the Sun's ever-changing surface and atmosphere in various electromagnetic wavelengths, far beyond what the human eye can see, scientists were able to reveal fascinating details that are normally invisible. The image was taken using a 19.3 nanometer wavelength, a type of extreme ultraviolet light. This specific wavelength corresponds to a temperature of around 1 million Kelvin, allowing us to observe the Sun's outer atmosphere, known as the corona, in remarkable detail. The corona is the glowing outer layer of the Sun that extends far into space. What's even more fascinating is that the corona is usually hidden from our view, except during rare events like total solar eclipses. During these brief moments when the Moon perfectly aligns between the Earth and the Sun's bright surface, called the photosphere, is completely blocked. This allows the shimmering corona to become visible, creating a breathtaking halo of light. However, as stunning as the corona looks during an eclipse, it can't compare to the level of detail captured by the SDO. This technology allows scientists to examine the Sun's features in ways that were impossible before, making it a vital tool for understanding the star that fuels life on Earth. Let's dive deeper into the incredible features of the Sun, focusing on the layers just beneath its outermost atmosphere, the corona. At a scorching temperature of 20 million Kelvin, we can observe some of the Sun's most intense and captivating phenomena. Among them are solar flares, those brilliant, fiery bursts of energy that can both mesmerize and alarm us. Solar flares are massive explosions on the Sun's surface where it ejects vast amounts of electromagnetic radiation into space. These powerful events happen when magnetic fields twist, snap, and rearrange themselves in a sudden, chaotic burst of energy. The source of this drama lies in the Sun's plasma, a churning, electrified soup that generates these magnetic fields. It's as if the Sun's restless nature fuels these awe-inspiring fireworks. Take, for example, a particularly active week back in August 2022, when solar flares lit up the Sun with spectacular intensity. But solar flares are only part of the story. Another fascinating feature of the Sun's atmosphere is something called coronal holes. These appear as darker patches on the Sun's surface when viewed with extreme ultraviolet light. Unlike the surrounding areas, coronal holes are cooler and less dense, and they behave quite differently. Their magnetic fields are open, allowing streams of solar wind, charged particles, to flow freely into space rather than looping back to the Sun's surface. When these solar winds reach Earth, they interact with our planet's magnetosphere, creating one of nature's most dazzling displays: auroras. These shimmering lights, often seen near the polar regions, are a direct result of the Sun's influence on our planet. Extreme ultraviolet light plays a crucial role in uncovering these hidden wonders of the Sun. It lets us see things that are invisible to the naked eye, revealing a vibrant and ever-changing outer layer filled with even more incredible phenomena. For instance, there are solar filaments, also called solar prominences. These are enormous glowing ribbons of gas that arc out from the Sun's surface, held in place by magnetic forces. One of the most amazing sights is the huge loops of hot gas that rise from the Sun's surface. These loops, called solar prominences, are so big that they make Earth look like a tiny dot in comparison. They can stretch hundreds of thousands of kilometers into space, farther than most people can imagine. While they can form in just one day, some prominences stay in place for months, floating in the Sun's outer atmosphere, known as the corona. In one striking example, a solar prominence winds its way upward from the Sun's surface into its atmosphere. This movement, shown in sped-up videos, clearly reveals how quickly the sun's strong magnetic fields move the hot gas. Considering the huge size of these loops, the speed at which they shift and twist is truly astonishing. The sun's atmosphere has something similar to rain. Not all the charged gas sent into the corona gets pushed out into space. Some of it cools down and falls back to the sun's surface as bright streams of what scientists call coronal rain. This rain is incredibly beautiful but unbelievably hot, still reaching millions of degrees. It sparkles as it falls, but don't let its beauty fool you. It's anything but gentle. However, not all of the sun's gas falls back. Sometimes the sun's tightly coiled magnetic fields snap, releasing huge amounts of energy. When this happens, a coronal mass ejection, CME, occurs, sending billions of tons of gas into space. Watching a CME happen is breathtaking. In sped-up footage, you can see it building up in the sun's lower regions before bursting out suddenly. These eruptions can affect Earth, as the gas and particles they release can interfere with satellites, power grids, and other technology. Scientists study these amazing solar events using tools like NASA's Solar Dynamics Observatory, SDO, which takes pictures of the sun in extreme ultraviolet light. One type of light often used is 30 nanometers, which helps show detailed views of the corona. Timing these observations is important because the sun's activity changes in an 11-year cycle, which affects how often these events occur. The sun's behavior becomes even more fascinating when viewed in different types of light. For instance, comparing two pictures of the corona taken at the same time, but in different wavelengths, reveals striking differences. One image, taken at a temperature of 600,000 Kelvin, shows the calmer corona with smooth loops. The other, taken at a blazing 2 million Kelvin, highlights the active, energetic parts of the corona. These side-by-side views show how varied and lively the sun's activity can be, depending on how we look at it. This layered complexity shows us how much we still need to learn about our closest star. What might seem like a simple solar event often turns out to be a chain reaction of connected processes. Now let's dive further into these secrets by looking at the sun in yet another wavelength of light. The transition region of the sun is a fascinating, paper-thin layer that acts as a boundary between the sun's outermost atmosphere, the corona, and the chromosphere, which is the closest layer of the atmosphere to the sun's surface. Despite being only about 100 kilometers thick, roughly the distance of a short road trip, this region is home to some of the most extreme temperature changes in the solar system. Here, the sun's temperature skyrockets from a relatively cool 8,000 Kelvin to an astonishing 500,000 Kelvin. To put this in perspective, the molten lava flowing from a Hawaiian volcano at a blistering 1,443 Kelvin is no match for the lower end of the transition region, which is nearly 6 times hotter, and at the upper end, it's a jaw-dropping 346 times hotter than that fiery lava. If we venture further down, we arrive at the chromosphere, a 700-kilometer thick layer that lies just above the sun's surface. Imaged in stunning ultraviolet light at 170 nanometers, this layer is a dynamic, ever-changing spectacle. One of its most captivating features is the presence of spicules, plasma jets that behave like long blades of grass swaying and dancing in the solar wind. These fiery jets shoot upward at breathtaking speeds of up to 100 kilometers per second, nearly 282 times the speed of sound. They can stretch nearly 10 kilometers into the solar atmosphere, towering even higher than Mount Everest, and live brief but dramatic lives, appearing and disappearing within just 5 to 10 minutes. For years, spicules remained a mystery. Scientists debated how these magnetically charged plasma jets could break free from the sun's powerful magnetic fields. Then in 2017, a breakthrough occurred. A team of researchers created a highly detailed model and discovered that the secret to spicules lay in neutral particles, tiny components previously overlooked. Initially, scientists didn't think neutral particles mattered because they don't carry a magnetic charge. But when these particles were included in the model, something incredible happened. The neutral particles gave the charged particles a surprising boost, almost like a helium balloon rising in the air. This newfound buoyancy allowed the plasma to break free and soar into the solar atmosphere, creating the mesmerizing spicules we observe today. The chromosphere, it's the second layer of a star's atmosphere, positioned between the photosphere below and the solar transition region and corona above. While the term is most often used to describe the sun's chromosphere, it can also apply to similar layers in other stars' atmospheres. In the sun, the chromosphere is an extraordinary glowing layer stretching 3,000 to 5,000 kilometers, about 1,900 to 3,100 miles, in height, just a tiny fraction of the sun's radius, yet essential in its dynamics. Its lower boundary, where it meets the photosphere, is a smooth, even layer. From this region, thin, jet-like structures called spicules emerge, shooting streams of hot plasma upward through the chromosphere and into the corona. These spicules can extend as far as 10,000 kilometers, 6,200 miles, into the outer atmosphere. What makes the chromosphere truly fascinating is its deep red glow, caused by emissions in the Haar spectral line of hydrogen. This red hue becomes especially striking during a solar eclipse, when the chromosphere briefly appears as a glowing rim around the sun. Scientists study this layer primarily by analyzing the electromagnetic radiation it emits, including light from ionized calcium. For example, the chromosphere shines vividly in the violet region of the spectrum at a wavelength of 393.4 nanometers, a phenomenon known as the calcium K line. The chromosphere is not just a passive layer, it's a dynamic, constantly changing region. Its spicules and shimmering light play a key role in linking the cooler photosphere below to the blazing million-degree corona above, making it an essential part of the sun's complex and captivating atmosphere. Chromospheres have been spotted on many stars beyond our sun. In some cases, especially with massive stars, the chromosphere can cover a surprisingly large part of the star. For instance, the chromosphere of the supergiant star Antares is incredibly vast. Its thickness is about 2.5 times greater than the star's radius. On the sun, the chromosphere's density thins out drastically as you move away from its center. Near the inner edge, it starts at about 2+10·4 kgm3, but drops dramatically to less than 1, 6×10·11 kgm3 by the outer boundary. This is a decrease by a factor of 10 million. The temperature also shifts curiously. It begins at around 6,000 K at the inner boundary, dips to a chilly 3,800 K, and then skyrockets to over 35,000 K near the outer edge, where it meets the sun's corona. Scientists are still puzzled about what causes this sudden temperature rise, calling it the coronal heating problem. Compared to the sun's photosphere, the chromosphere is about 10,000 times less dense, and it's a staggering 100 million times thinner than Earth's atmosphere at sea level. Because of this extreme thinness, the chromosphere is usually invisible. Its faint reddish glow only becomes visible during a total solar eclipse, when the sun's much brighter photosphere is temporarily blocked. The chromosphere's colors range from soft pink to deep red, giving it an otherworldly beauty. Without special tools, though, this delicate layer remains hidden, overpowered by the intense light of the sun's surface. The chromosphere has a fascinating and colorful nature. Its light is dominated by specific wavelengths, or emission lines. One of the strongest is called the H-alpha line, which occurs at a wavelength of 656.3 nanometers. This wavelength falls in the red part of the light spectrum, giving the chromosphere its distinctive reddish glow. The H-alpha line is produced when hydrogen atoms release energy as their electrons jump from a higher energy level, an equal sign 3, to a lower one, an equal sign 2. The chromosphere is full of intriguing features and activities. One of the brightest areas in this layer is known as a plage, a hot, glowing region linked to magnetic fields. Another striking feature is spicules, which are like tiny jets of gas that shoot up from the chromosphere, rise for a few minutes, and then fall back down, all within about 10 minutes. Advanced instruments, like the SUMA on the SOHO spacecraft, have revealed fascinating patterns in the solar chromosphere. For instance, waves or oscillations occur there at regular intervals, usually every 3 minutes. These waves, which involve the movement of plasma, are especially noticeable in the higher parts of the chromosphere. Interestingly, while certain frequencies of oscillations are not seen in the lower atmospheric layers, much faster waves, with cycles as short as 10 seconds, have been detected in the hotter regions of the sun's atmosphere by instruments like TRACE. At the edges of the sun, we can see plasma loops in the chromosphere. These loops, unlike the hotter solar prominences, are relatively cool, with temperatures around 100,000 Kelvin, 0.1 million degrees. These structures are highly dynamic. They can appear and vanish within an hour or expand rapidly in just 10 to 20 minutes. Observations from Skylab in 1976 provided detailed studies of these loops, showing how their behavior changes as their temperatures rise. When they heat up to over 1 million Kelvin, they stabilize and evolve more slowly, becoming part of the sun's corona. Images of the chromosphere often show a network-like pattern of bright cells, surrounded by darker regions known as the internetwork. These bright cells resemble the granules seen on the sun's lower layer, the photosphere, and are caused by heat convection. Chromospheres aren't unique to the sun. Almost all stars except white dwarfs have them. They are particularly noticeable in stars that are cooler and more magnetically active, including certain types of dwarf stars and giant stars. To measure chromospheric activity on other stars, scientists use a tool called the Mount Wilson S index. This index helps identify and study how active the chromospheres of stars are, shedding light on their magnetic behavior and overall dynamics. Now, let's take a closer journey into the sun's fascinating atmosphere. As we move deeper into the sun's lower atmosphere, we eventually reach the photosphere, often called the sun's surface. This is the part of the sun we can see most clearly using visible light. To our eyes, the edge of the photosphere might look sharp and well-defined, but that's an illusion caused by the sun's enormous distance from Earth. The sun isn't solid at all. It's far too hot for matter to exist in solid, liquid, or even gas form. Instead, the sun is made entirely of plasma, a state of matter where atoms break apart into charged particles, ions, and free electrons. Plasma, often described as the fourth state of matter, makes up an astonishing 99.9% of the universe's matter and behaves much like a gas, but with unique properties due to its electrical nature. The photosphere itself is about 400 kilometers thick and serves as the outermost layer of the sun visible in this image. However, unlike the sharp edges you might imagine, the photosphere isn't a solid boundary. It's more like a glowing shell of gas-like plasma. This layer is the deepest part of the sun that scientists can study directly. If you look closely at the photosphere, you'll notice some darker areas, often on the left side of images. These are sunspots, regions that appear dimmer because they are slightly cooler than their fiery surroundings. However, don't be misled. These cooler spots are still unimaginably hot. Unlike the larger coronal holes that stretch across the sun's outer atmosphere, sunspots are small but fascinating windows into the sun's magnetic activity. Sunspots are interesting dark spots on the sun's surface that form in areas where magnetic fields are very strong. These magnetic fields hold heat under the sun's surface layer, called the photosphere, by slowing down the movement of heat. When we compare a normal picture of the sun to one taken in extreme ultraviolet light at the same time, a surprising pattern appears. Sunspots and solar flares are closely connected. Wherever there are sunspots, solar flares often burst out, showing a clear link between these two dramatic solar activities. It's almost like one naturally leads to the other. An amazing picture taken by the Swedish Solar Telescope on Earth shows the fine details of sunspots in visible light at a wavelength of about 400 nanometers. Around these sunspots, the photosphere is covered with constantly changing rough-edged patterns called solar granules. These patterns look a lot like the cracked surface of cooling lava. But unlike lava, these cells are huge. Each one is about 1,000 kilometers wide. Solar granules are the top layers of giant convection cells below the sun's surface. The bright spots in these granules are areas where superhot plasma rises from deep inside the sun to its surface. When this hot material reaches the surface, it spreads outward and cools down. The cooler plasma then sinks back into the darker edges of the granules, creating a constant cycle. This process is similar to the convection currents in Earth's mantle that move tectonic plates. The size and power of this process are truly incredible. It's a strong, endless flow of energy and matter that powers the sun and affects the entire solar system. Nature's way of recycling energy in such an active way is truly remarkable. On average, each granule on the sun's surface lasts only about 20 minutes, but in that short time, incredible things happen. The flow of gas within these cells reaches supersonic speeds of over 7 kilometers per second. This immense speed creates powerful waves on the sun's surface, almost like sonic booms rippling through its fiery landscape. Amazingly, these granules are visible in the full disk view of the sun when captured using a specific wavelength of visible light. At first glance, you might think the image looks grainy, almost like a low-quality photo from a high-tech space probe. But that graininess isn't a flaw. It's the granules themselves, patterns on the sun's photosphere, revealing its dynamic, bubbling nature. Scientists haven't yet discovered how to see deeper layers of the sun using either visible or invisible light. Much of what lies beneath the photosphere remains a mystery, hidden from view. However, by studying the sun across different light spectrums, we've uncovered incredible phenomena, like erupting solar flares, vast coronal holes, flickering spicules, dark sunspots, and constantly changing cells. These imaging techniques allow us to observe the sun in ways we could never have imagined just a few decades ago. The sun is alive with energy and motion, much of which would remain invisible without advanced imaging tools. Someday, we may invent technologies that let us peer even deeper into the sun's fiery core, tools we can barely conceive of today. Just as ancient civilizations could never have imagined the telescopes and spacecraft we use now, our future discoveries may be beyond anything we can dream of. For now, knowing that there's still so much hidden in the universe fuels our curiosity and sense of wonder. The sun, with all its secrets, is just one piece of a vast cosmic puzzle. What other mysteries might be waiting to be uncovered? Only time and science will tell. The solar cycle, also called the solar magnetic activity cycle, sunspot cycle, or Schwabe cycle, is an 11-year pattern of changes in the sun's activity. This activity is measured by counting the number of sunspots on the sun's surface. Throughout a solar cycle, the sun's radiation levels, the amount of solar material ejected, the number and size of sunspots, solar flares, and coronal loops all rise and fall in a regular pattern. The sun moves from a period of low activity to a period of high activity, and then back to low activity again. During each solar cycle, the sun's magnetic field flips, usually at the peak of solar activity. After 2 solar cycles, the magnetic field returns to its original state, completing a pattern known as the Hale cycle. People have noticed these solar changes for centuries, seeing them in the sun's appearance and earthly events like the auroras. However, it wasn't until 1843 that scientists fully recognized the solar cycle. The sun's activity, which is influenced by both the regular solar cycle and sudden irregular events, shapes the environment of space around our planet. This affects space weather and has an impact on technologies that depend on space-based and ground-based systems. Additionally, the sun's activity can influence the Earth's atmosphere and might even play a role in long-term climate changes. Predicting the solar cycle is a big challenge for scientists, as it has important consequences for space science and our understanding of magnetic forces in space and other parts of the universe. While there is broad agreement among scientists that human activities, like burning greenhouse gases, are the main drivers of global climate change, solar variations are considered to have only a minor role. The changes in solar activity observed over recent years are much smaller compared to the influence of greenhouse gases on Earth's climate. Each solar cycle lasts about 11 years, with the solar maximum being the period of most sunspots and the solar minimum being the time with the fewest sunspots. Each cycle lasts from one minimum to the next. Scientists have reconstructed the number of sunspots over the past 11,400 years by studying carbon-14 and beryllium-10 isotope ratios. The solar activity we've seen since the 1940s stands out as extraordinary. The last time the sun was this active was about 9,000 years ago, during a warm period known as the Boreal. The sun's current level of magnetic activity is something that has only occurred for about 10% of the past 11,400 years. Most of the earlier periods of intense solar activity were much shorter than what we are experiencing now. Fossil records show that the sun's activity has remained fairly stable for at least 700 million years. For instance, during the early Permian period, the sun's cycle length was around 10.62 years, and this was also true in the Neoproterozoic era. Before 2009, it was believed that there had been 28 solar cycles over the 309 years from 1699 to 2008, averaging about 11.04 years per cycle. However, new research revealed that the longest cycle during this time, from 1784 to 1799, might have been 2 separate cycles. If this is true, the average cycle length would drop to about 10.7 years. Over the years, scientists have observed cycles as short as 9 years and as long as 14 years. If the 1784-1799 period is indeed 2 cycles, then one of those cycles must have been less than 8 years long. Along with this, the sun's activity also varies in strength from one cycle to another. There are several lists of historical periods of unusually low solar activity, often referred to as grand minima, that have been proposed by researchers. Solar cycle 25 started in December 2019, and many predictions were made about its strength using different methods. These predictions ranged from very weak to very strong. One model, based on the physics of solar activity and data-driven simulations, predicted that the strength of the solar polar field during the cycle's minimum was accurate and forecasted a weak yet noticeable solar cycle 25. This cycle is expected to be similar to or slightly stronger than cycle 24. The same model also ruled out the possibility of the sun entering a period of inactivity like the Maunder minimum over the next decade. In early 2019, a group of experts called the Solar Cycle 25 Prediction Panel, which was formed by NOAA's Space Weather Prediction Center, SWPC, and NASA, reached a general agreement about Solar Cycle 25. After reviewing several predictions, they concluded that Cycle 25 would be quite similar to Cycle 24. They predicted that the solar minimum before the start of Cycle 25 would be long and deep, just like the one before Cycle 24. The solar maximum, when sunspot activity is highest, was expected to occur between 2023 and 2026, with a sunspot number ranging from 95 to 130, according to updated figures for sunspot activity. Solar Cycle 24 began on January 4, 2008, and remained relatively quiet until early 2010. This cycle featured 2 peaks in solar activity, known as a double-peaked solar maximum. The first peak reached 99 in 2011, while the second peak occurred in early 2014 at 101. Cycle 24 came to an end in December 2019, lasting a total of 11 years. Looking back further, Solar Cycle 23 lasted for 11.6 years, beginning in May 1996 and ending in January 2008. The highest number of sunspots recorded during Cycle 23 was 120.8, in March 2000, while the lowest was just 1.7. During this cycle, there were 805 days when the sun had no sunspots at all. The solar cycle is a reflection of the sun's magnetic activity, and many solar events are influenced by this cycle, such as sunspots, bright patches called faculae and plage, a network of magnetic features, and massive bursts of solar energy known as coronal mass ejections. When there are more sunspots, the sun's surface, known as the photosphere, becomes more active and emits more energy. Space satellites have been used to measure the sun's brightness over time and have shown that there is a direct link between the solar cycle and the sun's energy output. The difference in brightness between the peak and trough of the cycle is about 0.1%. On a shorter scale, when large groups of sunspots rotate into view from Earth, the sun's brightness can drop by up to 0.3% over about 10 days. On the other hand, the brightness can increase by up to 0.05% for several months due to the bright patches, faculae, linked to these sunspots. The most detailed data today comes from the Solar and Heliospheric Observatory, SOHO, a collaboration between the European Space Agency and NASA. One of its key tools, the MDI magnetogram, allows us to see the sun's magnetic field on its surface. As the solar cycle begins, sunspots first appear at mid-latitudes and then gradually move closer to the equator as the cycle progresses, until a minimum in solar activity is reached. This movement of sunspots is often shown in what's called a butterfly diagram. This diagram divides the sun's surface into horizontal bands, with each band representing a different latitude. Over time, the amount of the sun's surface covered by sunspots is tracked month by month and shown as color-coded bars on the diagram. While sunspots are the most noticeable signs of magnetic activity on the sun, changes in the sun's magnetic field also occur across the entire surface, though these changes are usually smaller in magnitude. Faculae are bright magnetic spots found on the sun's surface known as the photosphere. These features extend upwards into the sun's outer layer, called the chromosphere, where they are given the name plage. To study how these regions change over time, scientists often use a special method involving the SAR-2K line, which is a specific wavelength of light, 393.37 nanometers, that reveals details about the sun's activity. Faculae and plage regions are much more common than sunspots, appearing about 10 times more frequently. However, their relationship with sunspots isn't a simple one. These features don't always appear or behave in predictable ways when compared to sunspots. Additionally, plage regions are often linked to strong magnetic fields just beneath the sun's surface. These magnetic forces are an important part of the sun's overall activity, influencing space weather and even affecting Earth's magnetic environment. The Gleisberg cycle refers to a long-term pattern in the sun's activity, where solar cycles seem to grow and shrink in intensity over a period of 70 to 100 years, or roughly 7 or 8 solar cycles. It was named after the scientist Wolfgang Gleisberg. This pattern has been observed in the way the sun's magnetic activity changes over time. Scientists like Ilya G. Usoskin and Sami Solanki have discovered that these long-term variations in solar activity are connected to changes in magnetic fields in the sun's outer layers, the corona, and the surrounding space, the heliosphere. By studying carbon-14 and beryllium-10 isotopes found in tree rings and ice cores on Earth, they've been able to trace solar changes back hundreds of years. Additionally, by looking at historical records of geomagnetic storms, disturbances in Earth's magnetic field, they have filled in the gaps between the ancient isotope data and modern satellite measurements of solar activity. Using advanced models, scientists have been able to recreate these variations by applying equations that track the flow of magnetic energy from the sun's atmosphere into space. By combining data from sunspots, geomagnetic activity, and cosmic isotopes, they have been able to confirm that these 3 sources of information offer a consistent understanding of how the sun's activity changes over time. Another cycle, known as the Suez cycle or de Vries cycle, operates on a much longer timescale of about 210 years. It's observed in radiocarbon data, which helps track solar activity over centuries. This cycle is named after scientists Hans Eduard Suess and Hessel de Vries. Although researchers have found a connection between the rates at which radioisotopes are produced and the 400-year sunspot record, there's not much direct evidence of the Suess cycle in the sunspot data itself. The 11-year solar cycle is believed to be half of a larger 22-year cycle called the Babcock-Leighton solar dynamo cycle. This cycle involves a constant back and forth of energy between 2 types of magnetic fields on the sun, the toroidal and the poloidal. These magnetic fields are influenced by the movement of solar plasma, which helps drive the dynamo process and provides energy for it at every stage. At the peak of the solar cycle, the sun's outer poloidal magnetic field, a magnetic dipole, is at its weakest point, while the internal toroidal magnetic field, which has a more complex quadrupolar shape, is at its strongest. This toroidal field is created by the sun's differential rotation, which occurs in a region called the tachocline. As the cycle progresses, plasma from the sun's convection zone pushes this internal toroidal magnetic field to the surface, where it emerges through the photosphere, creating pairs of sunspots. These sunspots align east to west and have opposite magnetic charges. Interestingly, the magnetic polarity of these sunspot pairs alternates with every new solar cycle, a pattern known as Hale's law. As the solar cycle winds down, energy shifts from the internal toroidal field to the outer poloidal field, and the number of sunspots decreases. At solar minimum, the toroidal field is at its weakest, sunspots are fewer, and the poloidal field is at its strongest. When the next cycle begins, the differential rotation of the sun turns the poloidal magnetic energy back into the toroidal form, but with an opposite polarity compared to the previous cycle. This process keeps repeating itself, and in an idealized scenario, each 11-year sunspot cycle marks a switch in the sun's large-scale magnetic field polarity. Studies of the solar dynamo process suggest that certain plasma movements inside the sun, like differential rotation, meridional circulation, and turbulent mixing, play an important role in recycling the toroidal and poloidal magnetic fields. The relative strength of these processes affects the memory of the solar cycle, which helps scientists predict future solar activity. In particular, simulations have shown that the solar cycle's memory is short, lasting only for one cycle, meaning accurate predictions can only be made for the next cycle, not beyond that. This idea has been confirmed through observations. Although the tachocline was once thought to be essential for generating the Sun's magnetic field, recent research has raised questions about this. Observations of brown dwarfs, which are similar to the Sun but lack a tachocline, show that these objects also have large-scale magnetic fields and experience cycles of magnetic activity. Unlike the Sun, brown dwarfs do not have a radiative core or tachocline, but instead they have a convective envelope that stretches from their core to their surface. This suggests that the Sun's magnetic activity might be generated in its convective envelope, rather than relying solely on the tachocline. Space is becoming more and more crucial to our modern world, so it's not surprising that the Sun's outbursts, like solar storms and coronal mass ejections, CMEs, can have a big effect on our technology up there. Scientists now can predict when a solar storm, also known as a geomagnetic storm, will reach Earth. They can often give us a heads-up day, or even weeks in advance. This early warning allows astronauts to take shelter and protect themselves from dangerous levels of radiation, and it also gives engineers the chance to power down sensitive equipment on satellites to keep them from getting damaged. Solar radiation can cause unexpected electric currents to form in the satellite wiring, and if those systems haven't been switched to a safe mode, it could overload them and cause serious damage. But there's another surprising effect of these solar storms. They affect Earth's atmosphere. When radiation from the storm reaches us, it causes the atmosphere to warm up, just slightly. This warming makes the atmosphere expand, and that expansion can impact satellites in space. Normally, objects in space don't experience drag because the atmosphere up there is so thin. This allows satellites to orbit for a long time without needing constant adjustments. However, while it's true that satellites in low Earth orbit do need to use fuel occasionally, about 4 times a year, to correct their paths, there's still a tiny bit of atmospheric drag up there. When a geomagnetic storm hits, the atmosphere swells upward, and satellites in low Earth orbit have to adjust their orbits every 2 to 3 weeks to avoid being pulled down by the extra friction. Sometimes, though, this isn't enough to keep them in orbit. In 1989, a powerful geomagnetic storm hit Earth, causing a major disruption. It was so intense that it knocked NASA's Solar Maximum mission right out of the sky. The satellite, which was designed to study solar flares, suddenly slowed down due to a shift in the atmosphere, which increased its density. Ironically, the mission was supposed to be studying solar activity, but it was brought down by it instead. This wasn't the only time this kind of thing happened. The North American Aerospace Defense Command, NORAD, often has to move hundreds of satellites to new orbits after geomagnetic storms, as these storms can push satellites off their original paths. The increased radiation from these storms can also affect the Earth's ionosphere, filling it with charged particles or plasma. This can interfere with GPS systems, making them less accurate. What might seem like a small error on your GPS, showing you as being on a street across from where you are, could be the result of a geomagnetic storm. Every 11 years, power grids around the world prepare for these storms, because they can induce electric currents that risk overloading the system. Even amateur radio operators and airline pilots see their communication systems suffer, as high-frequency radio waves are often blocked or deflected by the stronger charged ionosphere. These effects can make technology less reliable, and with the next solar maximum expected in 2025, we can expect more of these disruptions. As space weather becomes more active, areas like Canada experience an increase in auroras, those beautiful, colorful lights dancing across the night sky. People who chase these auroras often report seeing them far more often, even twice a month, during the most active parts of the Sun's 11-year cycle. Now, you might think that all these solar effects are limited to machines and technology, but you'd be wrong. The Sun's activity can also affect living things, including us. The solar cycle impacts ecosystems and even human health. When the Sun is at its quietest, during a solar minimum, it releases less solar wind, which means Earth's protective heliosphere, the bubble of solar energy that shields us from cosmic radiation, is weaker. While most of this radiation is absorbed or deflected by Earth's atmosphere, the little that does get through could potentially cause changes. One theory, though still uncertain, suggests that this increased radiation could be forming tiny nucleation sites in the atmosphere, leading to the formation of more clouds. This could influence our weather patterns. Even if that's not happening, space weather can still slightly raise global temperatures. While the increase may be less than half a degree, it's enough to have noticeable effects, especially for animals that rely on temperature to decide when to start their mating season. So, while solar activity may seem like just an issue for machines, it can affect life on Earth in unexpected ways. Studies on birds have revealed that in warmer years, they tend to lay their eggs earlier than usual. In a fascinating 2009 study by Dutch researchers, it was discovered that even the timing of egg laying in blue tits was influenced by something unexpected: the number of sunspots. The researchers themselves were puzzled by this, as birds can't look up at the sun to count the spots. Despite this mystery, the study found a clear connection when observing 5 different bird groups. Interestingly, this isn't just a phenomenon that affects blue tits. Birds like homing pigeons, which are sensitive to magnetic changes, also adjust their flight paths based on the sun's activity during its 11-year cycle. But it's not just birds being influenced by the sun. Humans too seem to be impacted by solar cycles, though it's still not fully understood. For example, a 2011 study in the Netherlands examined 2 decades of health data from nearly 1.3 million women. It found a notable spike in certain cervical health problems following the solar maximum, the period when the sun's radiation is at its strongest. A similar, though much smaller, study on men revealed that after solar maximums, they experienced slight increases in body temperature, pulse rate, blood pressure, and respiration. Though the study was smaller and less conclusive for men, it was still intriguing. But the effects aren't just physical. Mental health seems to be influenced by the sun's activity as well. A study from 2006 analyzed data from 237,000 people in the main Medicaid database, covering the years 1995 to 2004. The results showed that people born during periods of heightened solar activity had a higher likelihood of developing mental health issues. So the solar cycle at the moment of your birth might have a subtle influence on your life's course. Not quite the basis for astrology, but it does suggest that solar events could affect us in ways we don't fully understand. It's important to note, however, that these potential health effects are very small. One researcher emphasized that it took studying hundreds of thousands of patients to even notice the effects. So while the sun's cycles might have a slight impact, they shouldn't keep you from living your life. Looking ahead, we are approaching a solar maximum, expected in 2025. But for those concerned, it's not all bad news. The same research suggested that solar maxima could also boost creativity and adaptability in some individuals. Perhaps it was during one of these solar peaks around 880,000 years ago that human brains underwent a mutation that allowed us to think abstractly and develop consciousness. If that's the case, then we might owe much of our ability to perceive the universe to these solar cycles. Without them, we might not be who we are today. Imagine a world where space suddenly can carry sound. In this strange new situation, we can hear the sun from Earth, even though the sun is about 152 million kilometers away on average. It might surprise you to learn that the sun is extremely loud, so much so that it's easy to hear from our distant planet. If we could hear it, it might sound something like this. There is no sound in space. What we're hearing is a reconstruction, where scientists have turned the vibrations, frequencies, and sizes of the sun's energy into sound waves, allowing us to imagine what it might be like if sound could travel through space. This sound is what we might hear if there were an atmosphere to carry the waves, and it has a buzzing quality, almost like an electric hum. It's like a generator, or perhaps something with a faintly radioactive tone. That's fitting because, after all, we're talking about the sun, an enormous ball of nuclear fusion. The sun's power output is huge. It releases about 3.85 x 10 circumflex 26 watts of energy every second. That's 1 million times more than humanity produces in an entire year. This massive energy production directly affects how loud the sun would be if we could hear it. To give you an idea of this, imagine the device you're using to watch this. Now, connect it to the speakers used in the loudest rock concerts and play this noise at full blast. The sound would be at 110 decibels, dB, which is extremely loud. While you could survive a short burst of this sound, If it played non-stop in the sky, everyone on Earth would probably go deaf without ear protection. The sound near the sun's surface would be even stronger. Experts guess it could reach around 270 dB, an unimaginably loud volume. To put that in perspective, every 10 dB increase represents a 10-fold increase in sound strength. So, 270 dB is 100 million times louder than the maximum sound level our atmosphere can handle. No sound can exceed 190 dB in Earth's atmosphere because of physical limits on how sound waves behave in different materials. The sun's noise would go way past that limit. Sadly, many of the sun's sounds would mix by the time they reached us, turning into a blur of noise, losing the detailed differences that we could hear up close. To enjoy the sun's sounds, we'd need to get much closer, entering that ear-shattering zone. But for now, let's set aside the mind-blowing volume and focus on the special patterns of sound that the sun might create. If we were to travel in a spacecraft towards the sun, we would begin to notice a change in the sound's consistency. Instead of a steady buzz, we'd hear something much more complex and changing. The solar wind is a constant flow of charged particles released by the sun, traveling through the solar system. This event is one of the sun's biggest mysteries. At first, it seems like the particles are shooting outward from the sun because of the huge energy of nuclear reactions at the sun's core. However, by the 1960s, scientists made an important discovery. By observing, they found that particles in the sun's atmosphere, or corona, were moving at an average speed of 145 meters per second. But outside the corona, these same particles were speeding along at a much faster rate of 618 meters per second. This meant that particles with enough speed to escape the sun's surface were drifting into space, only to be sped up to faster speeds by something unknown in the corona. The cause of this speeding up is still a mystery today. The corona holds another mystery too: it's extremely hot. While it's expected that the sun's core would be the hottest part, with the temperature cooling as you move away from the center, that's not the case with the corona. The surface of the sun is around 5,600 degrees Celsius, but just a few kilometers above that, in the corona, the temperature jumps to nearly 2 million degrees Celsius. Something within the corona is both sending solar wind into space and causing this extreme heat, though scientists haven't figured out exactly what's causing it yet. It's believed to be linked to the sun's magnetic fields, but the details remain unclear. As we travel closer to the sun, approaching the boundary between the corona and the space beyond, we start to hear a new, eerie sound, the sound of L-mode waves. These waves are made by tiny, vibrating particles of plasma, set in motion by light itself. As the plasma moves through small funnels on the sun's surface, it creates these vibrations, much like the sound a kettle makes when it boils. These waves are the result of countless streams of plasma shooting outward from the sun. The sun's outer surface is filled with hot material that rises from the core, cools, and then sinks back down. This rising and falling material, or the forces at work within the sun, create strong magnetic fields. These fields collect the plasma and send it speeding into space, creating the solar wind. As these waves travel outward, they don't all move at the same speed. The faster parts of the waves move ahead of the slower ones, causing the sound to spread out and create what is known as dispersive waves, adding to the strange, fascinating symphony of the solar wind. These waves are filled with small bursts of sound where fast waves coming from behind meet slower waves already moving ahead. Over time, these waves balance out into the hum we heard earlier. But there's one final sound that might help us solve the entire mystery, a sound that holds some interesting clues. Deep within the sun's boiling, rough atmosphere called the corona, we can finally start detecting what's known as Whistler mode waves. Whistler waves are like distant echoes of high-energy events, traveling through the plasma of a celestial body's magnetic field. On Earth, we hear these waves whenever lightning strikes. But it's not just thunder you hear. A ripple travels through Earth's magnetic field, and if you have the right equipment, you can pick it up from miles away. To get a sense of how these waves sound on Earth, here's an example. Just a few small, brief cracks and whistles, nothing too unusual. Now, let's listen to what these waves sound like in the sun. The difference is striking. What starts as scattered, brief clicks quickly becomes a loud, chaotic wail. This change tells us that the sun's magnetic field isn't just experiencing occasional lightning-like bursts. Something much more continuous is happening, turning individual events into a constant roar. Scientists are still working on figuring out what's causing this steady noise, but one possibility is something called magnetic reconnection. Magnetic reconnection may sound harmless, even boring, but its name hides the true power behind it. The sun is like a tightly wound ball of magnetic field lines, constantly shifting due to the churning plasma at its core. The magnetic forces at play are huge. Sometimes, as magnetic field lines move away from the sun, they can merge with other field lines, forming the iconic loops we often see in images of the sun. However, when these field lines meet, chaos erupts. A powerful realignment happens, and everything above the arc must shift to stay balanced. The magnetic field lines, no longer bound to the sun, form their arcs, shooting off into space with the force of a massive rubber band snapping back. This incredibly fast-moving release of energy is called a nanoflare, and it heats the sun's corona to millions of degrees in just a few seconds. Scientists have only recently gained the technology to detect nanoflares, and they're still unsure if the nanoflares they've observed are truly what they expected. Still, they seem to cause the intense heating they had hoped for. This remains an ongoing mystery. We don't yet fully understand everything about nanoflares and the sun's magnetic activity, but it's not entirely far-fetched to think that these explosive events could explain why the sun's corona is so incredibly hot and why it releases such powerful solar winds into the solar system. To account for the constant solar wind and the shift from single cracks to a continuous roar, the force behind this phenomenon must be widespread throughout the sun's entire corona. The sun holds many secrets, and the Parker Solar Probe, which has been collecting these sounds, is still on its mission to uncover more. Currently, the probe is only a few years into its 7-year journey, and it continues to gather important data with every orbit. Hopefully, it will reveal even more sounds and answers that will allow scientists to better understand the mysteries of the sun. In 1846, something truly remarkable happened in the world of science. A French astronomer and mathematician named Jean-Joseph Leverrier made an extraordinary discovery. He found the planet Neptune using nothing but the power of mathematics. Leverrier had been carefully studying the movement of the 7 known planets at the time when he noticed something odd about Uranus. It wasn't following the expected path based on Newton's laws of gravity. The planet's movement seemed off, and Leverrier believed the only explanation was that another planet, located far beyond Uranus, was influencing its orbit. He worked out a mathematical model to predict where this hidden planet must be and pinpointed its exact location in the night sky. What happened next was nothing short of astounding. Leverrier shared his prediction with his colleague Johann Gottfried Galle, who immediately trained a telescope on the spot Leverrier had identified. Within just an hour, Galle found Neptune, almost exactly where Leverrier had predicted. The scientific world was stunned by the accuracy of his calculations, and Leverrier was hailed as a genius for his brilliant deductions. So it wasn't surprising that a decade later, in 1858, Leverrier predicted the existence of a 9th planet using the same mathematical approach. This time, the scientific community took notice once again. However, Leverrier wasn't the first person to suggest that there might be another planet out there. As far back as the year 1600, the German astronomer Christoph Scheiner had observed a strange dark spot crossing the sun, which he believed could be a planet. Later investigations showed that this was likely just a sunspot, but other sightings were recorded over the years, sparking curiosity about the possibility of more unknown planets. In 1818, an astronomer named Capel Loft, followed by Johannes Hevelius in 1819 and J.W. between 1822 and 1837, all reported seeing something strange, an object, or even several objects, moving around the sun. These sightings were reported at least 12 times, creating a lot of excitement. As more reports came in, people began to come up with ideas about what this mysterious object could be. In 1846, French astronomer Jacques Babe suggested calling it Vulcan, after the Roman god of volcanoes, fire, and metalworking. The name seemed right because any planet closer to the sun than Mercury would be extremely hot. Mercury itself already experienced scorching temperatures of 427 degrees Celsius, so a planet even closer would be even hotter. However, Despite these many claims, proving the existence of such a planet remained difficult. What made the claims by astronomer Urbain Le Verrier stand out was the careful method he used in his discovery. In 1845, before he famously discovered Neptune, Le Verrier had been asked by the director of the Paris Observatory to apply Isaac Newton's laws of physics to the orbit of Mercury, to see if everything lined up as it should. Le Verrier worked carefully to create a theoretical model of Mercury's orbit around the Sun based on Newton's laws. When astronomers then observed Mercury's actual orbit, however, they found something strange. It didn't match the predictions. Le Verrier thought his calculations might have been a little off, so he tried again, conducting a more detailed study in 1859. This time, he used more observations of Mercury to improve his model. Yet again, his predictions were still slightly off, by only 45 arcseconds per century, but it was enough to show something was wrong. Confident in his revised calculations, Le Verrier suggested that the difference could be caused by the pull of a hidden mass, either a planet or possibly a group of asteroids moving Mercury off course. Given his previous success in finding Neptune, many astronomers trusted his judgment. The scientific community quickly turned their attention to the skies, eager to find this mysterious planet. But finding a planet so close to the Sun was a huge challenge. The bright sunlight made it nearly impossible to detect any light reflected from such a small planet. To solve this, astronomers used a different method. They tried to spot the planet by observing the shadow it cast as it crossed in front of the Sun. In 1859, Edmond Modeste Leal even claimed to have seen just that, a darkening across the Sun's surface, suggesting the existence of this hidden planet. Lescarbot, a French amateur astronomer and doctor, was an enthusiast who worked with simple tools in his homemade observatory. On December 22nd, he claimed to have seen something remarkable, a small black object moving near the Sun. Excited to share his discovery, he wrote to Le Verrier, a well-known astronomer. Curious and eager, Le Verrier decided to investigate the claim himself. Without warning, he boarded a train and arrived at Lescar's home. After questioning Lescar about his observations, Le Verrier decided the man was being honest. Together, they announced the discovery to the scientific community. The newly discovered object was named Vulcan, and the announcement caused a lot of excitement. Scientists praised Lescar, giving him many honors, including France's highest award, the Légion d'honneur. He was invited to speak at important meetings of scholars. But as exciting as the discovery was, there was a big problem. Vulcan didn't exist. Le Verrier's calculations placed Vulcan 21 million kilometers from the Sun, completing its orbit every 19 days and 17 hours. With such clear predictions, finding it again should have been easy. However, when astronomers aimed their telescopes at the Sun at the predicted time, Vulcan was nowhere to be seen. Le Verrier was confused but determined. Reports started coming in from other astronomers who claimed to have seen Vulcan at various times in the past. Some of these accounts were unclear or years old, but Le Verrier used them to improve his calculations. Even with adjustments, Vulcan remained invisible. Then came a serious challenge to Vulcan's existence. Emmanuel Lear, another French astronomer, reported that he had been observing the Sun with a much stronger telescope at the exact time Lescar said he saw Vulcan, and he saw nothing. This cast major doubt on the discovery. Occasionally, respected scientists claimed to have spotted it, keeping the debate alive. In 1878, two well-known astronomers reported seeing a reddish object in the same area during a solar eclipse. Their confirmed observations revived interest in Vulcan, but it was never consistently found again. The final blow to Vulcan's existence came from Albert Einstein. For years, scientists had been searching for Vulcan because Newtonian physics suggested it had to exist to explain Mercury's unusual orbit. Many astronomers, expecting to see Vulcan, thought they had, but Einstein took a different approach. In 1915, Einstein introduced his revolutionary theory of general relativity, which explained that the space around massive objects like the Sun bends. Using this new idea, Einstein showed that Mercury's orbit could be fully understood without adding an extra planet like Vulcan. Einstein's predictions matched Mercury's movements perfectly, something Newtonian physics couldn't do. With Einstein's theory confirmed by tests like the 1919 solar eclipse observation, Vulcan's existence was disproven. If a planet the size of Vulcan had been that close to the Sun, it would have affected Mercury's orbit in ways Einstein's equations ruled out. A stunning photograph captured a 22 degrees solar halo floating over Gross-Kotenberg, Germany. The term 22 degrees doesn't refer to temperature, but to the angle of the halo. To imagine this, picture drawing an imaginary line from one point on the halo to your eye. Then, draw another line from the Sun to the same point of view. The angle formed between these two lines measures exactly 22 degrees, giving the phenomenon its name, the 22 degrees halo. But halos don't stop there. There are also 46 degrees halos, which are larger but fainter than their 22 degrees counterparts. These amazing light rings can also form at night, lit by the moon instead of the sun. Known as moon rings or winter halos, they're technically the same phenomenon as solar halos, with the only difference being the light source. Sometimes you might notice that the area inside the halo looks darker compared to the outer sky, a striking effect often called a hole in the sky. This happens because as light bends and spreads through ice crystals, none is reflected directly back toward the light source, creating this illusion of dimming. But halos are just the beginning. These optical wonders can take on a variety of beautiful and surprising forms. Bright spots of color, upside-down rainbows, and even nighttime rainbows. To truly appreciate their beauty, let's dive into the fascinating science behind them. Most circular halos are created by sunlight or moonlight interacting with ice crystals in thin, wispy clouds called cirrus or cirrostratus clouds. These clouds float high in the atmosphere, 5 to 10 kilometers above the Earth's surface, where the air is cold. This means halos can form anywhere on the planet, at any time of year, even in the hottest places. The ice crystals responsible for halos are tiny, usually less than 10 micrometers long, and have a very consistent size and shape. This consistency comes from the molecular structure of ice itself. Water molecules are made of 2 hydrogen atoms and 1 oxygen atom. In liquid water, these molecules are always moving, and their bonds keep breaking and reforming. But when water freezes, this motion slows down a lot, and the bonds between the molecules become fixed, forming a hexagonal pattern known as a tetrahedral arrangement. This molecular arrangement is what shapes the ice crystals into flat, hexagonal plates or column-like structures. Even though their shapes are different, all ice crystals share one key feature. The angles between their faces are the same. This uniformity in their geometry, rather than their size or weight, allows millions of crystals to bend and scatter light with incredible accuracy. It's this perfect alignment of light and ice that creates the dazzling halo effect we see. Halos can sometimes be quite colorful, and this happens because ice crystals in the atmosphere bend light in special ways. The red and blue light wavelengths shift at slightly different angles, creating a beautiful rainbow effect, often forming halos that spread out at a 22 degrees angle. You may notice 2 colorful spots on either side of the sun, and these are called parhelia, or sundogs. Sundogs form when ice crystals, shaped like hexagonal plates, align horizontally in the sky. Some of these crystals are thin and plate-like, while others are shaped like columns with a hexagonal cross-section. When the plate-shaped crystals fall through the atmosphere, air resistance causes them to turn on their sides, with their flat faces facing the horizon. Larger plates wobble a bit more than smaller ones, which changes how tall the sundogs appear. The wobble makes them look more vertically stretched, depending on the size of the crystals. Sometimes, sundogs are accompanied by another phenomenon called a circumzenithal arc, which is like an upside-down rainbow, creating a cheerful smile shape in the sky. This arc forms only when the sunlight and the orientation of the ice crystals are perfectly aligned. Light enters the top of the hexagonal crystals and exits from the sides, but this can only happen when the sun is less than 32.2 degrees above the horizon and more than 5 degrees. The way light bends inside the ice crystals is very precise, which makes circumzenithal arcs much sharper and clearer than regular rainbows. If you're lucky, you might even see a version of these arcs at night, called lunar circumzenithal arcs, which appear when the moon is bright and low in the sky. These optical wonders aren't just limited to Earth. Circular halos have been spotted on Mars, as seen in an image taken by NASA's Perseverance rover on December 15, 2021. Scientists think these halos might be caused by carbon dioxide crystals in Mars' cold, thin atmosphere, or a mix of CO2 and water ice. The discovery was exciting because before this, scientists didn't know halos could form on Mars. The size and appearance of the halos can tell us a lot about the types of ice crystals in the Martian atmosphere, and studying halos on Earth and other planets might help us understand the atmospheres of those distant worlds. Researchers are planning to continue studying these halos, not only on Mars, but also on other moons and planets, to learn more about their atmospheric compositions. So now that you know about some of the most well-known ice halos and the fascinating optical phenomena that accompany them, you might want to know how to spot them yourself. First, look for cirrus clouds, the wispy, high-altitude clouds that contain the tiny ice crystals needed for halos to form. Next, check the sun or moon, but always be cautious not to look directly at the sun, as this can damage your eyes. While rainbows appear opposite the sun, forming around the anti-solar point in the sky, ice halos tend to form near the sun or moon. Even though halos often appear during fair weather, they can also signal the approach of a storm. So, if you spot a halo, it's a good idea to head indoors soon after to stay safe and cozy as the storm rolls in. If the weather is clear but rain is predicted in the next 24 hours, keep an eye on the sky. Your chances of spotting a halo will be higher. And remember, ice halos can appear anywhere on Earth, so if you look up often, you're likely to see one eventually. There are still many other rare halos out there, and we might discover even more in the future. The world of ice halos is full of surprises. Sungrazers are a special type of comet that get very close to the sun, brushing its surface as they pass by. As they travel through space, their orbits bring them so close to the sun that they often enter its large atmosphere, known as the corona. These comets usually have long, oval orbits that take them hundreds to thousands of years to complete. Because their orbits are so stretched out, they build up incredible speeds as they approach the sun, sometimes reaching up to 0.2% of the speed of light. A huge speed, especially when you consider that we're talking about objects the size of houses. Most of these sungrazers come from a single large comet that broke apart hundreds of years ago. This broken comet has created a group of smaller pieces which continue to pass by the sun over time. As the largest pieces of this original comet pass near the sun, they too break apart into even smaller bits. These comets tend to follow the same path through space, which is why scientists believe most of them come from the same source. One of the brightest comets of the last 1,000 years, Comet Ikeya-Seki, was likely one of these pieces. It was so bright as it neared the sun that it could even be seen during the day. You may also remember Comet Lovejoy, another piece of the original comet, which appeared in 2011. Though it wasn't as bright as Comet Ikeya-Seki, it still made a spectacular show in the sky, particularly in long-exposure photographs. Even though scientists didn't expect Comet Lovejoy to survive its close encounter with the sun, it made it through mostly intact, despite being severely affected by the heat and gravity. This was surprising because the comet passed through the sun's atmosphere, which is over 1,000,000 degrees Celsius, for over an hour. A similar thing happened with Comet Dyson, which was expected to be bright and visible to the naked eye in 2013. While it didn't live up to the hype, it still made an impressive show for the sun-observing satellites. As it passed by the sun, it began to fade, and scientists couldn't be sure if its core survived. If it did, it's unlikely to have any volatile materials left, with most of the comet's substance likely evaporating into space as dust. Some of the largest sungrazer comets are a few hundred meters across, and they are some of the most exciting ones to study. However, smaller comets, often only tens of meters wide, weren't discovered until they came into view of sun-observing satellites. Unfortunately, many of these tiny comets get completely vaporized by the sun as soon as they pass too closely, disappearing almost immediately after they are spotted. In some cases, they travel behind the sun and disappear, never to be seen again. When we are lucky enough to observe them in real time, we can sometimes witness their vaporization as they approach the sun. The heat near the sun is extreme, and its gravity is incredibly strong. As these icy comets draw closer, the intense heat causes them to evaporate almost instantly. The sun's gravity also tears apart the rocky parts of the comets. Our close observations of comets show that they are often fragile and porous, sometimes little more than a pile of rubble held together by gravity. When these comets get too close to the sun, The combined forces of heat and gravity are so overwhelming that even the largest sungrazers come out heavily scarred, their structures weakened or broken apart. Something interesting happens when a sungrazer comet flies close to our Sun. At that same moment, a coronal mass ejection, CME, often happens, which is a burst of solar particles. This happens a lot, but scientists still argue that there's no proof the comet causes the CME. They think these comets, being pretty small, don't have enough weight to affect the Sun in such a big way. For now, these events are considered coincidences. Still, scientists find sungrazers exciting because even though we can't send machines deep into the Sun's atmosphere since it's too hot, these comets go there for us. They offer a great chance to study the Sun's magnetic fields, which helps scientists predict CMEs and space weather better. As the comet moves by, its tail wiggles and heats up, turning into plasma, a hot, glowing gas. This plasma can be seen with special UV cameras on satellites. Plasma reacts strongly to magnetic fields, and scientists think the tail's movement shows how the plasma interacts with the Sun's magnetic field lines. Right now, space weather is not fully understood, but as more comets fly through, we'll learn more about the Sun. While we've captured some amazing videos of sungrazers, those cameras weren't even built for that purpose. Now imagine looking at the sky and seeing not one but two suns. It would be an amazing sight to watch both sunsets together. This isn't that unusual. About a third of star systems have two or more stars. Let's say we kept our current sun and added a second one. Stars come in many sizes, from small, cool red dwarfs to huge, hot blue supergiants. In a system with two stars, they orbit each other around a shared center. If the two stars are about the same size, their orbit could be round or oval-shaped. But if one star is much bigger, the center of orbit shifts closer to the larger star. Imagine putting a red dwarf, which is much smaller than our Sun, in a tight orbit with the Sun. Even though red dwarfs are only about 7.5% the mass of our Sun, their presence would still have a big effect. From Earth, it would seem like the red dwarf orbits the Sun, sometimes passing in front of it and other times being hidden behind it. Having two stars would shorten our year because their gravity would change things, and Earth would need to move faster to avoid getting pulled into the stars. If we wanted to keep moving at the same speed, Earth would have to move farther away. The extra heat from the second star could make life impossible, though how hot it gets would depend on the star's type and the greenhouse effect. Seasons would change completely. Earth's tilt wouldn't matter as much as the position of the second star. In winter, when the second star is farther away, it could get extremely cold. But in summer, when the second star is closer, it could become unbearably hot. Red dwarfs often create massive solar flares, far stronger than anything our Sun produces. These flares could knock out satellites and power systems regularly, like giant EMP bombs. If the second star were a larger one, like a blue supergiant, life on Earth would face even bigger problems. Blue supergiants are extremely massive, many times larger than our Sun, and their strong stellar winds could strip away Earth's atmosphere quickly. If a giant star like this replaced our Sun, it would swallow Earth and reach as far as Saturn. These stars are so powerful that life on Earth would be impossible. In rare cases, Earth could still survive in a two-star system with a supergiant. In some systems, the stars are far apart, sometimes over a light year, so each star has its planets. If Earth were in one of these systems, it would only orbit one star, and the second star would just look like a bright dot in the sky, having little effect on climate or solar winds. But even in this setup, the supergiant would still be dangerous. These stars are unstable and often explode as supernovae. A supernova just 1 light-year away could release enough radiation to destroy all life on Earth. In a two-star system, the day-night cycle would also be very different from what we have now. If one star was close enough to Earth, it could disrupt the normal cycle, causing long periods without any darkness. Even if the second star was far away, life would still face constant problems, from powerful flares to extreme temperature changes. So while the idea of seeing two suns sounds exciting, the reality would be far from ideal. From deadly solar flares to extreme weather and the risk of a supernova, a second sun would cause more harm than good. In the end, Earth's single steady sun is exactly what makes life possible. In 2009, NASA announced a bold mission to study the sun up close, the Parker Solar Probe. This spacecraft was launched on August 12, 2018, using the powerful Delta IV heavy rocket. Its goal is to get closer to the Sun than any spacecraft ever has, using 7 passes by Venus over nearly 7 years to slowly shrink its orbit. At its closest, it will come within just 6.16 million kilometers of the Sun, deep inside the Sun's outer layer called the corona. Temperatures can climb to an astonishing 1,400 degrees Celsius. At such heat, most materials would melt instantly. To survive, the Parker Solar Probe is protected by an 11-centimeter thick carbon-based heat shield. This shield not only survives the intense heat, but also reflects much of it, reducing the spacecraft's exposure. The heat shield always faces the Sun, acting as a protective umbrella for the delicate instruments behind it. The mission faces more than just heat challenges. So far from Earth, the spacecraft must mostly operate on its own. It can't always point its antenna toward Earth because its main task is to keep the shield aimed at the Sun. During these periods without communication, the spacecraft will manage its equipment, store data, and wait for the chance to send its findings back to Earth. Another important mission, the Solar Orbiter, was launched on February 10, 2020, after 8 years of planning. This spacecraft, carried into space by an Atlas V rocket, also uses flybys of Venus and Earth to adjust its orbit around the Sun. Its closest approach will be about 43 million kilometers from the Sun, farther than the Parker Solar Probe, but still in an area where temperatures can reach a scorching 500 degrees Celsius, 13 times hotter than sunlight on Earth. The Solar Orbiter's heat shield, made of titanium with special coatings, is about 40 centimeters thick. Although not as strong as the Parker probe's shield, it is enough to protect the spacecraft on its crucial mission. Getting near the Sun is incredibly hard. It takes 55 times more energy to reach the Sun than it does to get to Mars. This is because Earth moves very fast, about 30 kilometers per second, 108,000 kilometers per hour, in its orbit around the Sun. To reach the Sun, a spacecraft has to cancel out most of this sideways motion, which requires a huge amount of energy. That's why both the Parker Solar Probe and Solar Orbiter needed 2 of the strongest rockets available at the time. The main goal of both missions is to solve the Sun's mysteries, especially its strange corona. This outer layer, made of superhot plasma, stretches millions of kilometers into space. Plasma is a state of matter so hot that atoms lose their electrons, leaving behind charged particles. The Sun's surface, or photosphere, has a temperature of about 5,500 degrees Celsius, but the corona is shockingly much hotter, between 1 and 3 million degrees Celsius. Scientists are still puzzled by why the corona is so much hotter than the surface below. The Sun's corona is hard to observe directly because it is much dimmer than the Sun's surface. However, during a solar eclipse, when the Moon blocks the bright surface, the corona's faint, glowing arms become visible. Despite its delicate beauty, the corona is extremely thin, millions of times less dense than Earth's atmosphere. These missions, with their daring designs and advanced technology, aim to uncover the corona's secrets, the behavior of solar winds, and the Sun's magnetic field. Learning about these features could reveal important details about the Sun's effects on Earth and the rest of the solar system, and possibly explain the forces at work in stars across the universe. The Sun constantly sends out streams of hot gas and energy into space, known as the solar wind. While this solar wind isn't very strong or thick, the Earth's magnetic field works like a shield, pushing most of it harmlessly away. However, some of the particles in the solar wind are pulled toward the Earth's poles, where they crash into oxygen and nitrogen in our atmosphere. These crashes create energy that we see as colorful lights called auroras, like the famous northern and southern lights. But the Sun doesn't always act the same. Sometimes its magnetic field changes in a big way, releasing huge amounts of energy from its outer layer, called the corona. These explosions, known as coronal mass ejections, CMEs, send billions of tons of charged particles into space in one event. If one of these CMEs hits Earth's magnetic field, it can cause a geomagnetic storm. Smaller storms create beautiful auroras, but bigger ones can cause serious damage. The strongest geomagnetic storm ever recorded was the Carrington event of 1859. If a storm like that happened today, it could create chaos, breaking satellites, shutting down power systems, and acting like a huge EMP, electromagnetic pulse bomb, over a large area. In today's world, Where we depend on electricity and the internet, even a few hours without power could lead to major issues. Experts estimate that a Carrington-sized storm could cause damage worth trillions of dollars. What makes CMEs even more dangerous is how fast they move. They can reach Earth in just 17 hours, which might not give us enough time to prepare, turn off power plants, or protect important systems. In 2012, a massive CME barely missed Earth by 9 days. If our planet had been in a slightly different position in its orbit, the result could have been disastrous. This close call is a strong warning that we need to better understand and predict solar activity. It's not a matter of if another event like this will happen, but when. To study the sun's corona and predict solar storms more accurately, scientists have launched 2 special missions, the Parker Solar Probe and the Solar Orbiter. While their work overlaps a little, each spacecraft has unique abilities. The Parker Solar Probe is flying closer to the sun than any spacecraft in history, right into the corona. Because it's operating in such extreme heat, it focuses on studying the particles in the corona and where the solar wind begins. However, it can't take pictures of the sun up close because no camera can survive such extreme conditions. On the other hand, the solar orbiter stays farther from the sun and carries both particle detectors and telescopes. This allows it to take clear pictures of the sun's surface and atmosphere. Its orbit also lets it watch solar storms as they form over several days, which isn't possible from Earth. Together, these probes are helping scientists understand the sun's behavior and improve our ability to predict harmful solar storms. On September 27, 2020, the Parker Solar Probe made an incredible journey, coming as close as 13.5 million kilometers to the sun. This was the nearest any spacecraft has ever been to our star. Not only did it break this record, but it also became the fastest human-made object in history, reaching an astonishing speed of 466,000 kilometers per hour. Even though the probe was still quite a distance away, the data it sent back has already provided valuable insights into the sun's magnetic field and the way solar winds form in the corona, the sun's outer atmosphere. It also revealed that certain magnetic fields from the sun sweep through the solar atmosphere, causing solar winds to speed up by as much as 500,000 kilometers per hour. Another fascinating discovery made by the Parker probe was the detection of a dust-free zone about 5.6 million kilometers from the sun. Scientists believe this phenomenon occurs because the sun's powerful radiation vaporizes cosmic dust particles in that region. Meanwhile, the Solar Orbiter, another important spacecraft, has already sent back its first stunning images of the sun. These pictures showed something intriguing: campfires. These are small explosions on the sun's surface caused by disruptions in tiny magnetic fields. The Solar Orbiter also captured the closest images ever taken of the sun's surface from a distance of just 77 million kilometers. By studying particles along its orbit, scientists are hoping to unlock even more secrets about the sun and space itself, deepening our understanding of the forces that shape our solar system. A Dyson sphere is an idea for a huge theoretical structure that surrounds a star and collects a significant amount of its energy. It's not something we've built or even seen yet. It's more of a thought experiment. The purpose of this idea is to explore how an advanced civilization that travels through space might solve its energy problems once the power it needs is far more than what its home planet can provide. Right now, only a tiny portion of the energy a star releases ever reaches the surface of planets orbiting it. So by building a massive structure around the star, this civilization could gather a much larger amount of that energy. The first modern version of this idea came from Olaf Stapledon in his 1937 science fiction novel Star Maker. It was later expanded upon by physicist Freeman Dyson in a 1960 paper titled Search for Artificial Stellar Sources of Infrared Radiation. Dyson suggested that such structures would make sense as civilizations grow and their energy needs increase. They would become essential for their survival in the long run. If astronomers ever detected something like a Dyson sphere around a distant star, it could be a sign that an intelligent alien civilization is out there, using advanced technology to harness its star's power. Since Dyson published his paper, many different designs have been proposed that involve creating artificial structures or a series of them to surround a star. These ideas have appeared both in scientific studies and science fiction, often referred to as a Dyson sphere. In fictional accounts, these structures are usually imagined as a solid shell completely enclosing a star, though this was considered impossible by Dyson himself. The idea for what would later be known as the Dyson sphere was inspired by Olaf Stapledon's 1937 science fiction novel Star Maker. Freeman Dyson, a physicist and mathematician, was the first to give a formal definition to this concept in his 1960 paper Search for Artificial Stellar Sources of Infrared Radiation. In this groundbreaking paper, Dyson suggested that as a highly advanced civilization's energy needs grew, it would eventually need to find a way to capture energy directly from its star. He theorized that this could be done by building a system of structures orbiting the star, designed to collect its vast amounts of energy. Dyson believed that this energy harvesting system would turn sunlight into far infrared radiation, which could then be detected by astronomers on Earth. His theory proposed that a search for such infrared signals could potentially reveal the presence of intelligent life around distant stars. Dyson didn't provide a detailed plan for how such a system could be built, simply referring to it as a shell or biosphere in his paper. Later he explained that he wasn't imagining a solid structure at all. He clarified by saying, "A solid shell or ring around a star is mechanically impossible. The kind of biosphere I had in mind was more like a loose collection or swarm of objects, each moving in its independent orbit around the star." This idea is often called a Dyson swarm. However, in 2013, Dyson admitted that he regretted the concept being named after him. Energy collectors, inspired by Dyson's vision, would surround a distant star to capture and re-radiate its energy. The energy they release might have different wavelengths from those typically emitted by the star, mainly because they would contain heavier elements not naturally found in the star's composition. If the amount of this unusual energy were large enough, it might be possible to detect such an alien megastructure from far across space. This could point to the existence of what scientists call a Type II Kardashev civilization, a highly advanced society capable of harnessing the energy of an entire star. SETI and Fermilab have both searched for signs of unusual infrared light from stars similar to our Sun. Fermilab, in particular, identified 17 potential candidates, though these were considered uncertain. By 2006, 4 of these candidates were labeled interesting, but still uncertain. Over time, additional searches found more potential signals, but none of them have been confirmed. On October 14, 2015, a group of citizen scientists from the Planet Hunters project noticed strange changes in the light coming from the star Kaisi 8462852. This sparked speculation that we might have discovered a Dyson sphere, a massive structure that could encircle a star and capture its energy. However, after further analysis, scientists concluded that the strange light patterns were likely caused by dust, not an advanced megastructure. In 2024, another search turned up 7 new potential candidates for Dyson spheres, but experts said more research was needed to be sure. While building a Dyson sphere is theoretically possible, creating a stable, large-scale structure around the Sun is currently far beyond our technological abilities. The number of spacecraft needed to build, transport, and maintain such a structure would exceed what we can do today. However, some thinkers like George Dvorsky have proposed using self-replicating robots as a way to make this feat possible in the not-too-distant future. Others have even suggested that Dyson spheres could potentially be built around other stars, like white dwarfs or pulsars, which might be easier to harness. Stellar engines are theoretical giant structures designed to capture and use energy from stars, often for specific tasks. For example, Matryoshka brains have been suggested to use this energy for advanced computing, while Shkadov thrusters would use it for propulsion to move spacecraft. Some of these designs are inspired by the idea of a Dyson sphere, a massive structure built around a star. In May and June of 2024, rumors started to spread that scientists may have detected signs of Dyson spheres in space. The 7 objects they focused on are all M-dwarfs, a type of star that is smaller and dimmer than our Sun, and they're located within 1,000 light-years from Earth. However, the researchers were careful not to make exaggerated claims. Despite their caution, many news outlets ran with the story. Other explanations, like the idea that the infrared signals might be from galaxies hidden behind dust, have been suggested by experts as more likely reasons for the discovery. The idea of Dyson spheres has its roots in science fiction. In Olaf Stapledon's 1937 novel Star Maker, he described a futuristic scenario where every solar system is surrounded by a gauze of light traps designed to capture and use solar energy. This concept inspired Freeman Dyson, who even suggested that a Stapledon sphere might be a more fitting name for the idea. While fictional Dyson spheres are usually imagined as solid, continuous shells surrounding a star, Dyson himself argued that such a structure would be practically impossible to build. In many stories, Dyson spheres are used as big dumb objects, a plot device that serves as a mysterious and awe-inspiring element in the story. Dyson spheres have been featured in many science fiction stories, often as background elements. One of the earliest appearances was in the 1964 novel The Wanderer by Fritz Leiber, where aliens use these spheres to surround multiple stars. The concept also appears in the Saga of Cuckoo, a book series written by Frederick Pohl and Jack Williamson between 1975 and 1983. In Bob Shaw's 1975 novel Orbitsville and its sequels, one of the stories takes place inside a Dyson sphere. The idea was also featured in the 1992 Star Trek The Next Generation episode Relics, where the USS Enterprise becomes trapped inside an abandoned Dyson sphere. In a 2011 interview, Dyson, the scientist behind the idea, said that while he liked the Star Trek episode, he thought the depiction of the sphere was unrealistic. Michael Jan Friedman, who wrote the novelization of the episode, felt that the Dyson sphere was mostly a plot device with little actual importance in the episode itself, so he expanded on the concept in his book, Version of the Story. Dyson spheres have also been explored in other science fiction works, including Tony Rothman's The World is Round, Somtow Sucharitkal's Inquisitor series, Timothy Zahn's Spinneret, James White's Federation World, Stephen Baxter's The Time Ships, and Peter F. Hamilton's Pandora's Star. Variations on the Dyson sphere concept have appeared in different forms, such as a single ring in Larry Niven's 1970 novel Ringworld, a half-sphere in Gregory Benford and Niven's 2012 novel Bowl of Heaven, and nested spheres, sometimes called Matryoshka brains, in Colin Capp's 1980s Cage World series and Brian Stableford's Asgard trilogy. Stableford pointed out that Dyson spheres are often used as plot devices or remain in the background of many stories, such as in Fritz Leiber's The Wanderer and Linda Nagata's Deception Well. He notes that in stories about space exploration, other concepts like Niven's Ringworld are more commonly explored. He offers two reasons for this. First, Dyson spheres are simply too vast and complex to tackle in detail, a challenge that was highlighted by Friedman. When he adapted Relics into a novel, he couldn't delve into the sphere because his book was limited to just 400 pages, and he had only about 4 weeks to write it. Second, for hard science fiction, Dyson spheres come with tricky engineering problems that complicate the plot. Specifically, inside a Dyson sphere, the force of gravity would be balanced out due to the way the structure is built, according to the shell theorem, so the usual force of gravity wouldn't work. To make things stay grounded on the inside surface, alternative methods like rotating the sphere are needed. But this creates another issue. The gravity would decrease near the poles of the sphere, which makes it hard to keep things firmly attached. Authors have tried to solve these problems with creative adjustments, such as the concept of cage worlds, Dan Alderson's idea of a double sphere, and Niven's smaller version of the ring world, all of which explore different ways to handle the challenges of Dyson spheres in storytelling.